My introduction to cryptocurrencies. So now that I've explained or given you a high-level overview of the workings of Bitcoin, what I would like to do in the second hour is explain how several aspects can be improved and what other later cryptocurrencies have done. So I will look at anonymity, scalability, and expressiveness. Anonymity is actually they're all very relevant to this workshop because they use zero knowledge proofs in particular to achieve anonymity, but also new proposals to get scalability. So let's start with anonymity. So I think we all agree Bitcoin is not anonymous because if you have a currency where everything is public, even if your name is not there, then you can analyze which payments are spent how, and you can do analysis of the transaction graph. And there's people in the room that do that. What kind of anonymity can you achieve within Bitcoin? So the first thing that was proposed is that if you want to somehow have coins that are not associated to you, why don't you send them to some centralized so-called mixing service, and then they mix the coins and then they give you back another random coin. Often they don't give you back any coins. So that was not a good idea. There's better ways to do this, and one of them is called CoinJoin. I'll show you quickly. And then I'll talk about approaches done by other cryptocurrencies. In particular, I think Monero and Zcash are the main anonymous cryptocurrencies today. So what is CoinJoin? CoinJoin is basically the simple idea that if you have a transaction which has inputs and outputs, then this is atomic in the sense that there's no link between which input goes to which output. So if Alice and Bob want to mix their coins, what they could do is that they put in the same amount of Bitcoin. So Alice puts 1 here and 2 here, and Bob puts 3 here. And they create 2 new outputs, 2 new coins with new public keys. And then no one can associate who owns which coin. And the nice thing about this is that because they need to provide their signatures on this transaction, no one can cheat the other because you would only sign a transaction which gives you back your money. Other types of anonymity that were proposed as well by Greg Maxwell is confidential transactions, where the idea is that you want to have a payment system where you hide the amounts that are transacted. So this is not compatible with Bitcoin, but this is, for example, now implemented in Monero. The big problem here is that if you hide the amounts that go in and that go out, then by, say, encrypting them, how can the miner check that you have not just invented new money in your transaction? So you need means to prevent that. You want that the sum of the input values equals the sum of the output values. And that's actually something that Dan Bonnet already talked about. You can use this, you can achieve this by using homomorphic commitments. Why? Because if your inputs and outputs are committed, and if they're, so now you don't sum the actual values but the commitments themselves, and if that evaluates to the same, then by the binding property, the security property of the commitment, you can deduce that the same amount of value went in that came out. So if I have time, I'll actually show you some details of that. Now, let's see what else Monero does besides hiding the amounts. So it's based on a proposal called CryptoNote that proposed 2 ways of making payments more anonymous, where one concerns hiding the spender of a transaction, and one is about hiding the receiver. So hiding the spender is done by a cryptographic primitive, and it's not here anymore. I would have been proud to give this talk with one of the inventors of it in the room, called ring signatures. And hiding the receiver is done by a concept called stealth addresses, which I'll quickly explain. So who knows what ring signatures are? Just a quick program. Okay. So the difference so in a standard signature you have a verification key and a signing key. And in a ring signature, what you can do is you can collect a ring or a set of verification keys. You make a signature that verifies with respect to this set of keys, and the guarantee is that one of the owners of one of the keys has actually made this signature. So one of the secret keys that are associated to these verification keys was used to make the signature. So the initial motivation for this was whistleblowing. So if you work for a government agency, you want to disclose some information. You don't want people to know who you are, but you also want to convince, say, the journalist that you are actually an employee there. What you could do is you collect a lot of keys of employees. You make a ring signature so people can be convinced that one of the employees signed. So you can basically hide among a set of other people. And that's exactly the idea of how you can hide the sender of a transaction. So in Bitcoin, remember we had a transaction had an input, and the input referred to one of the outputs of a previous transaction in the blockchain. Now if you, instead of using regular signatures, use ring signatures, what you do is say you're the owner of this unspent transaction output and you want to spend it. Then you just select random other UTXOs, and then you make a ring signature, sigma, which now guarantees that one of the unspent transactions in this blockchain has been spent. So it seems it gives you kind of an anonymity because you don't know which one was spent, but it seems to completely break the whole idea of double spending, because first of all, what is even an unspent transaction output? If someone put this inside a ring but didn't really spend it, it should remain unspent. So that's not clear. So there's no more real concept of unspent transaction outputs. There's only outputs that might have been referenced or not, but whether they were spent or not, you don't know. Also, this basically enables a very simple double spending attack. Say you've used your secret key here, you put it in a ring, you've spent this money, created a transaction, and then later you make another transaction and you use the same key again. How can people check if you don't know which one was spent? You don't know which one was double spent. So this is solved by not using pure ring signatures, but a primitive called traceable ring signatures, which allows you to link. So if you have a ring signature, it's completely anonymous of which of the keys was used to sign. But if you have two signatures that use the same key, then you can link them. So now people can, if they see a new signature, they can check whether it links to one of the old ones. And if so, it means that the key had already been used. And so they reject it as being a double spending. So that's implemented in Monero. It turns out that it's quite important of how you pick these other outputs among which you want to hide.
Is there analysis of this by scientists?
The primitive?
Of what Monero does?
Yes, because the first analysis showed that using some heuristics, correct me if I'm wrong, you can actually trace people, because like a simple heuristic was if you just put any transaction outputs in the blockchain, then most likely the actual one will be the ones that occurred latest. Also, if you have a lot of, you basically can infer things, right? If you know that this one, that one was spent, it can't have been another one, so you can eliminate and you can like do an analysis.
So can I step forward from Bitcoin?
Yes. But not as far forward as Zcash.
But depending on how much you're still linking, sometimes it's better not to promise.
I think it's been rather receptive to analysis. For example, they've now, I think, deployed in their wallet some measures on being more careful about how you pick the other.
Yeah, so they changed the coinage heuristic to adapt to the research. So.
It's a bit of a cat and mouse, but it might converge to something half reasonable. So it's not perfect anonymity, but certainly much more respectable than Bitcoin.
And enough anonymity for criminal activities. Okay, so so this allows you to hide when you're the spender. Actually, hiding as a receiver is a lot easier because if in Bitcoin every time someone wants to send you money, you create a new address and send them that address in private, then no one can trace you because all you see is random addresses on the blockchain. However, if you do that, then you cannot have, for example, be an NGO and publish a Bitcoin address for donations. You would have to interact every time you want to receive money. So that would, like, you can't have non-interactive payments where you have someone's account number and just send money to it. So that would be a disadvantage. And stealth addresses actually allow you to have both at the same time. So you can publish an address and people can use it to send you money without talking to you. But still, the payments they make to that address look completely unrelated to your address. And that, I think, is a cute trick that I'll show as one of the more technical things in this talk. So the idea is that so I have, let's say this is my address. I know the key for this address. I publish it. And if people want to send me money, what they do is they derive a related address from my address, which looks unrelated, and a transition key that allows me, if I get this key, to derive from my original key and this transition key, this new key for that address. Okay, that's the idea. So if someone sends me money, he sends it to an address which looks completely unrelated to mine, and he gives me some information that allows me and only me to derive the key to this new address. And then you send the money to this new address, and I know the secret key, so I own it. So this can be done using this Diffie-Hellman-Hart groups, I guess, to be precise. So we've seen this before. So you use a group over an elliptic curve. It has a generator, so some element g, and you can define x times g as adding g to itself. You want the discrete logarithm problem to be hard. So if I give you some element h, you cannot find the x such that multiplying g or adding g x times to itself gives you this element h. And this is what's already used in Bitcoin and other cryptocurrencies, namely for ECDSA, the elliptic curve digital signing algorithm, which is used in Bitcoin, or for Schnorr signatures, which is more popular now among newer cryptocurrencies. So your secret key is this scalar x, and your public key is secret key times generator.
Question from non-cryptographer.
Yeah.
Why something simple like the sender create public key and private key
You could do that.
together, and they send to the public key and encrypt the secret key and encrypts the secret key with my public key and
Yeah.
the public key.
Because then you would have payment on the blockchain, which belongs to you because you have the secret key, but it still belongs to the sender as well because he knows the secret key as well. So you don't want to be only one of many owners of the payment. That's why you do that. So in Bitcoin, an address is actually the hash of, but I'll ignore that, a public key for ECDSA, and the value x is your secret key. So in a stealth address, you actually have two group elements. Let's call them capital A and capital B. And you see in a minute why there must be two. It's actually exactly the reason I just said. So what does the receiver do? He chooses a random scalar y. He creates this transition key defined as y times g. So it looks like a Bitcoin public key for this secret key. And the stealth address, or the one-time address that is created will be the hash of small y times capital A, so the randomness he picked and this part of the receiver's public key, times the generator plus the other part of the public key. Okay, so for the cryptographers, you see, well, this is actually the Diffie-Hellman shared key between A and Y, which means that it's a value that you can obtain either by knowing small y or by knowing small a. So the sender has created it by knowing small y, but it's actually equivalent to small a times capital Y, which means that the owner of this address who knows small a can also compute this value. And if you look at this equation, you see that the secret key for this new address is actually a value that can be computed from the secret key of the old address plus this capital Y that must be sent to the receiver.
What's the point of B?
What's the point of B? So what if B was not there? Then the secret key for this new address would be small a times capital Y, which is this value which the sender knows. So you would send it to an address which would basically amount to the same as what you proposed, to have an address to which the sender still knows the secret key.
Would it be fair to think of B as just a random shift of the shared key that only you know?
Yeah, I guess you could do it like this, yeah. Okay, so as I said, this is the secret key belonging to the new address, and it's something that you can obtain from these two values. So that's Monero. It uses some cool crypto to hide different aspects of identities or amounts using different methods. And then I think in contrast, Zcash goes a very different route. It uses one big hammer to hide everything. And that big hammer is non-interactive zero-knowledge proofs as instantiated by ZK snarks. So it's based on the Zero Cash protocol by Ben Sasson, Chiesa, Green, Garman, Madras, Troma, and Virsa. Correct? It's a fully anonymous currency. Again, I'll ignore some details. And it uses these ZK snarks, and it's actually deployed as Zcash, and it's one of the 30 biggest in market capitalization, I think. So what's the idea? The idea is, so it basically goes back to the very first thing I showed you, namely serial numbers. Now a coin is a commitment to a serial number. Again, I'm skipping the actual details. And the idea is that you have on your blockchain, you have all the coins, which basically correspond to what would be transaction outputs in Bitcoin. And you commit to all these coins using a Merkle tree. So that's some concise representation of all of them, which allows you to actually prove to someone that something is there. And when you spend one of the coins, you create a new coin. It's like creating a new Bitcoin address, which again is a commitment to a serial number plus some secret information that only the owner knows. And what you do is you prove that you actually knew the secret, that you spent a coin that existed in the old state of the system, and that the value you transferred didn't create any new money, that you were the owner, and so on. And you prove this by using a ZK snark.
There's a list of coins that exist and a list of coins that have been spent, right?
Yes, I come to that. Yeah, exactly. So for now, this, again, it's like the strawman that doesn't work, because exactly for the same reason as in Monero, you cannot just use ring signatures, because you need some mechanism to prevent people from spending their coin twice. If all you prove is, I know some coin that belongs to me, and now that gives me the right to create this new coin, okay, but who can check that you haven't done this twice for the same coin? So how Zero Cash solves this problem is similar actually to these traceable ring signatures. Every time you spend a coin, you reveal its serial number. And the snark proof takes care of the fact that you've actually given the right serial number. So the state of the system is all the coins that ever existed, whether they're spent or not, plus all the serial numbers of all the coins that have already been spent. So it's somehow dual to Bitcoin, where the state of the system is represented by all the unspent transaction outputs. So you need to remember what is the money that's still in the system, whereas here you need to remember what's the money that's not in the system anymore. Okay, that's so you can do this efficiently using zero-knowledge snarks, and you get a completely anonymous cryptocurrency. There's small drawbacks to this. The first one is that, I mean, this has improved by using newer snark systems, that it's slow. I think in the beginning you had to compute the transaction that contained the snark, you had to compute for several minutes. Now it's like less than a minute.
It's a few seconds these days.
Yeah. A few seconds, okay, good. So that has improved a lot. Pardon?
Still very expensive compared to signing a small.
Yeah. And I guess the biggest drawback viewed from the Monero community is that it has these trusty parameters. So has anyone in the first 2 days, we didn't really get that far, right, to see structured CRSs. Did we see structured CRSs in the first 2 days?
No, I only mentioned the existence of reference strings in Tuesday morning as something that must be there, but I didn't distinguish between uniform and structured.
Yeah. So the problem is that this trusted reference string with respect to which these non-interactive proofs are made has a certain form, and it has a form that you can only compute if you know some secret value, which unfortunately, if you know that secret value, also allows you to prove false statements. That's why the zero cash people refer to it as the toxic waste, which is some value that you need to convince your users no one knows. Because only if no one knows this value, aka simulation trapdoor for the cryptographers, then you know that your system is sound.
So who's verifying these snarks? The people who want to get the coins transferred to them or something? Or?
Yeah, I mean, it's the same as why do you verify signatures in Bitcoin? Because you want to be sure that the view of the blockchain you have is correct and consistent, and here instead of signatures we have snarks. So it basically replaces what are signatures in Bitcoin. So if you start mining Zcash, then you would download the whole history, you would verify all these snarks. And if you remember the first 2 days, while these snarks are really, or can be hard and have been hard to compute, they're very, very fast to verify. That's why this actually scales and you can verify all the transactions that happen.
I guess my question was that individual users, like if the equivalent of, just say, Joe Blow on the street who has a crypto wallet, what's the difference between what that person has to do in Zcash versus Monero or Bitcoin?
I think it's similar to Bitcoin. If you're a full node, you have to you can check everything, but that's resource intensive. If you have other light clients for Zcash.
Depends on how much you care about privacy.
Yeah. For non-shielded transactions, I guess. Yeah.
So the user is not creating the snark, or?
The user is creating the snark. So if
The user is creating.
yes.
So the replacement is instead of signature, you create a snark.
Exactly. So I think you can view really the snark is whatever the signature does for Bitcoin is what the snark does for Zcash. Yeah.
So when I read this, I was under the impression that you actually have two chains. One is kind of public and one is anonymous. The anonymous one pays out to the public. Is that just like a design layer on top, or is that necessary? Because you said this is completely anonymous, so I'm wondering if you could just use the private chain.
So you're not referring to serial numbers versus coins now, right? Just to no. In actual, that's why I said I'm not going through all the details. In actual Zcash, there's two types of transactions. You have these anonymous transactions, but you also have regular transactions which don't give you privacy. So, but they live in the same blockchain.
They're not necessary.
But you don't think it's necessary? So
No, in the paper itself, we can describe it as if there is some base currency against which you can import, but that's just a literary instrument.
Okay.
Any more questions? Okay, so the problem is that you have this toxic waste. So if you just have the Zcash people say, here's the parameters, how do you know that they didn't keep the secret and then just create new money if they want some more money? What they did is they ran a big ceremony among very different types of actors and jointly computed these public parameters using multi-party computation, so that if there was at least someone honest among all these people, you can be sure that no one knows this toxic waste. What about, so this gives you soundness, so protection against someone counterfeiting coins. Interestingly, anonymity holds even if everyone in this ceremony was corrupt, thanks to this properties of snarks called subversion zero knowledge, where even if, as long as you check some consistency of the parameters, even if someone malicious created this CRS, anonymity would still hold. Okay, that's so much for anonymity. So the second property I wanted to talk about is scalability. So the Bitcoin blockchain is basically continuously increasing, and it's now over 230 gigabytes. So people asked whether there's a way of avoiding having better scalability. So in terms of how much information has to be stored, but also in terms of how you can increase throughput. So one of the proposals a few years ago, again by an anonymous author, I guess to add some mystical aura to it, was called Mimblewimble, and it promises to do what Bitcoin does, but in a more scalable way, in the sense that in Bitcoin, your blockchain stores the whole history of whatever happened, what happened since the beginning, since the Genesis block. And what Mimblewimble tries to do is only store in the blockchain the information that is relevant now. That is, what are the coins that exist in the systems, and cryptographic information that ensure that this is a coherent state of the system. Yeah. So remember, this is the picture for Mimblewimble. For Bitcoin. We have blocks. This is the blockchain now vertically. We have transactions. If I spend this output here in this new transaction, I give a signature that authenticates it with respect to this public key. Now the signatures ensure that if this is my transaction and only I know the secret key thanks to unforgeability, no one can spend it. And it also, since all the amounts are public, it also ensures that no one can just create a transaction that creates money by itself, because miners would not accept that. So remember, this is basically, if you download the whole blockchain, you go through everything, you verify everything, that all you care about in the end is what are the transactions that have not been spent yet. Because if you later see a new transaction, you just have to verify with respect to that set whether it spends one of these unspent transaction outputs. So drawbacks, all the transactions are public, so we have weak anonymity, and all data must be kept forever to have this public verifiability of the system, which leads to bad scalability. What would be good scalability? So look at, consider this chain of transactions where this transaction spends this output here, which spends this output, and so on. Then basically all you would care about is not which path this transaction output took to get here, because this transaction was spent anyway. So why can't we just erase it from the blockchain? Why can't we just say, well, whatever was here is now there, and forget about what happened in between? That would be kind of a memory-less blockchain. Can you do this in Bitcoin? Not if you want to have verifiability, because this signature verifies with respect to this public key and so on. So if you want to check that this transaction is legitimate, you have to check all the previous transactions. So this idea of cut-through, that you can just erase transactions that have happened in the meantime, but that are not that have been spent already, does not work in Bitcoin. And that's what Mimblewimble promises to do. So since I have, I'll go over it quickly. So this will be, I guess, the most technical part. I'll tell you when to join in again if you get lost on the way. So the starting point for Mimblewimble was confidential transactions. So remember, confidential transaction was, can I hide the amounts of input and outputs of a transaction? The way this is done, this is what Dan mentioned in his talk, using the type of commitments that you use to hide the values is called Pedersen commitment. And you have two generators, H and G, of your elliptic curve group. And a commitment is you put your value here, multiply it by H, plus some random value times G. And since this value is completely random, this C is a random group element, and this completely hides your value. On the other hand, if discrete logarithm is hard in this group, you cannot find a different representation of a coin C. So this gives you what's called binding. So if you have a commitment, there's really only one value that you can take out of it. So remember, the problem with hiding the amounts is that you have to have some mechanism that ensures that whatever comes out of a transaction, whatever's the money that you can spend afterwards, shouldn't be greater than what you put in. And the idea is that, as I mentioned on the slide before, that what these homomorphic commitments allow you to do is, instead of taking the values, summing the inputs and the outputs and checking whether they're the same, you just do the same thing with the commitments. And because they're homomorphic, this works. And because they're binding, this is secure. So if you look at the sum of the output commitments minus the sum of the input commitments, you can rearrange terms. So basically you get that this is a commitment to the difference of the sum of the values, with the randomness being the difference of the sums of the randomness. So if you choose the randomness correctly, then this sum here will be the zero element of your group. This is what confidential transactions does. Any questions? Yeah?
Sorry if I'm asking something stupid because I don't understand, but we started from some Genesis block and we have to believe like that we're looking at your Genesis block. Why not just do the same thing and say, well, we believe in the block, like block 1,000,000, it's a year old. We just believe in that block, write all the account balances at that point, and that's it, and dump the chain from before.
Yeah, I mean, there are these ideas of putting checkpoints into the blockchain. But the thing is, who is in charge of putting these checkpoints?
Who verifies the Genesis block?
It's part of, basically, it's part of the system. It's like hard-coded in your system. Of course, you could download like a faulty Bitcoin client, but that's kind of how you bootstrap trust in the beginning. Whereas the checkpoint is something where you're not sure if someone could have like forked around it or something, but at least the Genesis block is something. I mean, you need some basic anchor of trust in the beginning.
How is the new version of this software accepted? Because checkpoints could be part of the code, right?
Yeah.
What's the process to agree on the new code? Whatever it is, that process should also be certified.
Yeah. I guess, I mean, there's exactly that you can only reduce trust up to some point where you have to start, and then the question is, do you start from the Genesis block, or do you start, or like from some initial reference client that Nakamoto himself produced, or do you also accept later versions?
There are people that are called Bitcoin core maintainers.
My own guess of why that. I mean, I think the checkpoints is a very. I think it's an elegant thing to do, but I suspect one problem with that is that if you put in one block all the open accounts, then that is a message whose size is very different, and the network is used to multicast.
There's several problems with checkpoints. One is why should I trust the person writing the checkpoint? The other is
you can verify, right? The same way you verify a new block.
Yeah, but the second is, what if somebody comes with a longer path from the Genesis?
Yeah, you need to be a full node to join.
Basically, it's creating a new consensus for a new Genesis.
What if you, a priori, you choose that every 1 million blocks, there's going to be a checkpoint, okay? And it's just going to be a very, very big block because you write in it like all the open accounts. And you can check that block like all the others because you can just look back from the Genesis that it is the correct.
This is a spring cleaning, right? Every year we'll do a new ceremony. That's fine.
I think the problem is that at least sprinkling is expensive, and then the network is not designed to deal with this type of expensive things. It's designed to deal with blocks up to 2 megabytes or something like that.
Also, we should keep in mind we're in a regime where people typically do send to a new address whenever they need one, even though they already have one. So usually the number of accounts is on the order of the number of transactions.
Well, but I mean, yeah, you're saying put all the open, like put the whole UTXO set into a block?
Right, that was the proposal.
But I mean, it's like 3 gigabytes. Or I mean, no, it's more.
But it's still less than the entire chain.
No, but
Right, but
to
you're
get
not
consensus to believe on this UTXO, you need the root of trust, and the root of trust is the Genesis block, so you're not saving anything.
Yeah. Like, but I think this doesn't give you trust either, because if you just see, like, sorry, not that it doesn't give you trust, but there's a limited amount of trust that gives you too, because suppose you look at the Litecoin, suppose your client was configured to look at Litecoin instead of Bitcoin. Everything should check out. Like, this doesn't tell you whether you're looking at Bitcoin or Litecoin. You still need some kind of reference, initial reference. If the initial reference could have been the Genesis block, why can't it be this checkpoint from a year ago?
No, the Genesis block is an assumption that you're going to get it. No one is going to guarantee to you that you're going to get it right. If whoever gets it right is going to be able to run consensus, right? That's the guarantee. It's a setup assumption. Now, you cannot make like, I mean, you can, but then it's more setup assumptions. Like, it's really, if you think of the actual statement that you're making, it's if whoever gets the correct Genesis block is going to be able to do consensus with whoever else gets the correct Genesis block. That's the statement.
No, but you have to add the, whoever gets the Genesis block and the right software. So I don't see why these checkpoints you don't need to trust them more than you trust the code that you're running.
No, without the Genesis block, the correct software is useless.
No, what I'm saying is it's not enough to have the Genesis code. Block. You also need the right software. And the software changes over time. And it's distributed. I don't know how it is checked. But whatever, right? Because if you are installing the wrong software, it can do anything it wants.
Yeah. Maybe, yeah.
Let's discuss software.
I'll just, so this is for who's really interested. So you can do this balance checking by looking at commitments, and then you get a problem because you could create a transaction that's valid because it spends 2 1 and 1 bitcoins, and it creates -5 and 9 bitcoins, so the sums check out. So that's, again, referring back to Dan's talk, that's what you use range proofs for. So with every commitment, you need to prove that this value is actually contained in some interval of reasonable amounts. So you avoid these overflow problems. So here's what Mimblewimble does, and if you look at it first, then I guess you don't believe that this can be secure. So if you if you use confidential transactions on top of a Bitcoin-like system, then in order to spend the coin, you need to know the secret key that goes with the public key, so you can make the signature, and you need to know the opening, so the randomness here of this commitment, so you can then create a balanced transaction. Okay, so there's two informations now, where one is for authenticity, and one is basically for privacy. So what Mimblewimble proposes is, well, if this coin has some secret value anyway, can we just say this is the secret key for the coin and forget about signatures altogether? So this doesn't seem very secure, but it turns out it is. But the first problem we need to solve is that if this is the secret key of the coin, again, we have to make sure that the sender doesn't know the secret key of the coins that are created. But if we still use this equation to check well-balancedness and say there's only one input and one output, then the randomness has to be the same. So necessarily the sender knows the secret key. So this is solved in a slightly different way, which lets every coin have its independent randomness, which means that this sum here will not cancel out typically. So instead of getting the 0 element of the group, we get 0 times h if the transaction is balanced, plus some x times g. And so instead of checking whether this is 0, we interpret this as a public key, or in other words, we prove that we know an opening of this to 0, or in other words, we prove that we know the secret value x here. And it turns out that at the same time, this proof also guarantees authenticity of this transaction. So it guarantees that if you own that coin, no one else can spend it. So basically this one signature takes care of all the security properties that we want in some very magical way. Yes?
What is the signature on?
Signature, so here you can just assume the empty message or its own public key.
It doesn't matter what message it is.
Exactly, because
you can produce a signature.
Exactly, because it's, I mean, in the instantiation you could sign like the block ID or things like that. But the reason is that you actually, the property you need from it is not that it's a signature, but that it's a proof of knowledge of an opening. But since it's Schnorr signatures that are used to instantiate it, people talk about it as signatures. Okay, so basically what is the nice consequence of this is that if we have two transactions, so recall inputs are, now you can really think of them as being the coins, are commitments. You have this value x1, which is the difference of the sums, and the signature that says that yes, this transaction is well balanced. And if you have two of them, then not very excitingly, you can put them together. Basically, you can sum these two equations, so you get the sum of the joint outputs minus the sum of the joint inputs equals the sum of these single differences. Okay, that's basically a non-interactive version of coin join, because it can be done a posteriori and not while the users that create the transaction are present. So we get a new transaction which has again a similar condition for being valid, but now the magical part that happens and that allows you to do this cut through is the following. If you started with a transaction which has some output that was then spent in the second transaction, meaning that these two commitments here are the same group element, then what you can do is you can just erase it, and still your transaction will remain valid. Why? Because this equation would still hold, because you removed it here and here. Okay, so you can take a transaction, and if this transaction comes from transactions where one spent outputs of another transaction, then you can actually forget about them and your transaction still remains valid.
So this is all within a block before so this is the miner when it
This is
the block and it drops things before it actually commits them anyway.
Yes, but then what you can, so the thing is that yes, you have your blockchain, but then you can basically create a condensed view of the blockchain where you do all these cut-throughs, and that's your state of the system, and that's all you have to verify. Even if there is some history that was, of course, in the blockchain before, because if something's already only spent later on, then it will be here, but you have this verifiable global view of the system.
But if you find such things, as you prepare a block, you can still drop them and they're just never stored.
Yes, exactly. You could even, exactly. That would give you even better anonymity because it won't even appear in the blockchain. So we have actually managed to get something that everyone's in.
Where is this shorter chain stored?
So you can, I guess you just add a Merkle hash of it into every block, and then whoever wants to join, someone has to give him the actual full thing, and he can check it's the right commitment. Okay, so this means that basically, since every input to a transaction is an output of a previous transaction, if you just do it to all the transactions in the system, everything will cancel out. And how long can you do this? Well, until you hit a coin-based transaction, so a transaction where money was created. So basically, if you keep your blockchain basically is now the merge of all transactions, and everything that was spent cancels out. So everything that's left is, on the left-hand side, the only inputs that were not canceled out were the ones that are coin-based transactions, or where the money was created. And on the right-hand side, everything that's not cancelled out is everything that hasn't been spent yet. So this is your UTXO set. And then you have these values that allow you to verify that everything has happened correctly.
So what have I saved here? I still have to store the whole, if I want to verify that this is the state, I have to check all the history.
You can check.
If I'm a full client, I have to run the whole history.
No, you could just check the headers of the blocks.
I see.
Okay, in the interest of time, I'll rush on. So this was, yes?
Just not to let you rush. How the privacy compares between this and Zcash?
Worse, because if you have, so I mean, it's. I think people talk about it as solving a privacy issue, but I view it more as solving a scalability issue. So it happened. It hides the amounts. That's true, but I mean, if you know who some coin belongs to, and then you later see it being, I mean, you see which coin is spent when, right? Whereas in Zcash, you just know that some coin that existed was spent. So privacy-wise, I guess it's like, we prove secure that there is some limited form of privacy that you can prove, which is basically about the amounts that are transferred. But the main thing we prove secure is that no one can create transactions that creates money, and no one can steal anyone else's coins. Which I think is because like when you look at it and you say, oh, let's get rid of the signatures, that's really when you start doubting whether the thing is secure, and it turns out that yeah, it works. So since one of the topics of the program is zero knowledge proofs and snarks, other approaches is there's a proposal called Coda. I think the ISAC is not here anymore. Which basically uses snarks not for the zero knowledge property, which is why Zcash uses them, but for their succinctness. So the idea is, let's just show this by pictures. So suppose we have this was at the very beginning, this ledger where you have the account balances, and this one is a legitimate update of this if Alice confirmed that yes, she was okay with Bob now owning her Bitcoin, right? So here the idea is that how can you make everything concise? You use Merkle trees, so you commit to this list of accounts. So you have the root of your Merkle tree, which is just one hash function output. and now you give a proof that whatever is committed in this new commitment to a ledger was obtained legitimately from whatever was committed here, right? That's the idea. So you don't want to see what exists and verify why these things are true, but you only have this concise view, and the proofs guarantee you that these concise views are legitimate. So basically, when so you have your Genesis commitment, and then you could do proofs that everything happened legitimately. But that would mean that, of course, you save a lot because you only have a few group elements per block, but it would still grow as the blockchain grows. So what they actually propose is that you could do somehow a meta proof and say, if this is the current blockchain, then I don't prove all these intermediate steps, but I give you a proof that these steps exist. And that's what recursive application of snarks allow you to do. And moreover, if you now add a new block, then from this old proof you can derive a new proof that authenticates this new
How scalably in time?
This is, apparently it runs on a test net, but yeah, I don't have any numbers.
The main issue in latency is that you're doing a proof tree along the Merkle tree, but that can be pipelined across multiple blocks. So with each block, not only you're making progress on the main chain of proofs, but you're also merging in parallel proofs along the tree. And so it's actually not so bad in terms of latency.
But yeah, it's, again, a lot of details that I didn't mention. This is basically the rough idea of what you can do by having recursive snarks.
And you can do it zero knowledge too, right?
Yeah.
The cost doesn't...
for all these snarks that exist, zero knowledge is basically for free. Intuitively, why? Because if your proof is so succinct, it can't contain much information about your witnesses, right? But it turns out that what you do is you add a little bit of randomness and you get zero knowledge very efficiently. It's really the succinctness part that's the hard thing to get. Okay. In the last few minutes, let me mention again things that I've explained in a simplified form, how Bitcoin actually works. So it's not that you can only do transactions. You can actually do more complicated things. Because if you make a Bitcoin transaction, then it's not that you just put a public key there and say that whoever has a signature can spend this output. But what you do is you write the script and say whoever gives value so that this script executes can spend this output. So for example, if you send a Bitcoin to an address, remember an address is the hash of a public key. Then to satisfy this, you write the script so that you can satisfy it if you give a public key so that the hash is the address and the signature so that it hashes to the public key. But other things are possible, and let me just mention 3 of them. So for example, what you can do is you can create outputs so that you need, which are associated to several addresses or several public keys. So all of them or some subset of them has to sign. So you could imagine a company having all their wealth in a Bitcoin transaction, and then some qualified majority of the board has to sign in order to move this money. You could do that. Another type of script opcode is that allows you to create transactions that you can only spend after a certain amount of time has passed. And I guess the simplest kind of transaction is you can put a hash image there and say whoever has a pre-image can spend it. So this would be send money to a hash pre-image. So the first one, multi-signatures, allows you to do escrow transactions. So you could put the public key of someone you trust in there, and then in case of dispute, that person can side with whatever participant and then execute the payment. Pay to hash pre-image allows you to do a very cute protocol, which is called zero knowledge contingent payments, which I'd love to present, but I don't have the time. But the idea is basically that you solve the problem of fair exchange by using a blockchain. So as an example, suppose that I have a Sudoku that I really want to solve, but I don't manage to do it. So I post on the internet and say, whoever gives me a solution to this Sudoku, I'll pay them 1 Bitcoin. The problem now is that these people want the money before they send me the solution, and I want to see the solution before I give out the money. So how can we, like whoever goes first can lose. But using this one nice operation and some zero-knowledge proofs in the background, you can actually solve this over Bitcoin so that it's guaranteed that either I get the solution and the person gets the money, or no one gets anything. And finally, you can also, by using multi-signatures and this lock time, you can implement micropayments. And this allows you to, this is basically what this Lightning Network allows you to do. So I'll not go through it, but the idea is that if, for example, I want to offer someone to internet access and I charge them 1 cent per minute, then I cannot do this via Bitcoin because A, transactions are too slow, and B, I will probably pay more in fees than that 1 cent that I get. So the idea is that you can take, make payments offline, by what they call establishing a payment channel, and only when you open and close the channel will something actually end up in the blockchain. But still, all the security guarantees that you get in this channel, that no one can steal your money, that's bootstrapped from the blockchain. Okay, so that almost concludes the talk. Basically, these are types of very special kinds of smart contracts, which means that you can have conditions encoded on the blockchain that are executed automatically if certain things happen. So you can use blockchains to solve the problem of domain registration. You can use them for gambling, voting, all kinds of applications. But the question is, can you have one blockchain with which you can do anything you want? And that's basically the promise of Ethereum, a universal blockchain. How do they? How does this work? So in Ethereum, you have a built-in programming language, and as opposed to Bitcoin, which is very simple, it is actually Turing complete. So you can, in principle, write any code, any conditions that you want. You have user accounts, and you have this idea of contracts that you can upload to the blockchain. Anyone can make a contract. You can send money to contracts. These contracts can then send money elsewhere, access other contracts. They have their own storage, so they have memory in the blockchain. Yeah, code can send money, read and write storage, call other contracts. And the nodes, now in Bitcoin, these nodes, they checked whether the signatures were valid. Now they have to actually do whatever the smart contracts tell them the code to execute. So it seems that you get a problem here, because one of the reasons why the Bitcoin scripting language is so simple is because you want to avoid problems with, that go back to these people, namely that you don't know how long it will take to run the code. So in Bitcoin script, you know that you will execute very quickly. If you have a Turing-complete programming language, then you run into Turing-related problems like the halting problem. So what if you put a smart contract on that then the miners will just run into an infinite loop? That would be bad. And the way this is solved is that you just pay them. Like this is basically, if anytime you want the miners to do something, you pay them. So for every computation step that your smart contracts makes the miners work, you give them small amount of what is called gas. And this is my last slide. So what are I guess this links to the third workshop, Decentralizing Society. What are the big promises of blockchains and smart contracts? Is that you can get rid of intermediaries. You don't need banks anymore. You don't need courts of law if smart contracts work the way that people imagine them. and you could have services that now work in a centralized way, in a decentralized way. So you could have an Airbnb where there's no company charging money, but just users that do things collaboratively.